everybody. Birds are chirping today, so you might hear them in the background. But I wanted to talk to you today about some thoughts I had on logs. Sometimes there's so many log rules that things can get confusing, so I just wanted to kind of go through some ideas that I had that might help you remember what is going on with logs. So first, one way to think of a log is that a log essentially is explaining what's happening in the exponent. So we know that logs and exponentials are inverse functions. So when you think of a log, you almost always think of an exponent, or vice versa. When you think of an exponent, you also think of a log. For example, multiplication and division, those two go hand in hand. If you're multiplying, for example, by 7, then to undo that, you would divide by 7. So, and vice versa, right? So those two things go hand in hand. Addition and subtraction, they're also inverse functions of each other. They also go hand in hand. So you don't ever really just think of addition. You also think of addition and subtraction because ultimately they're kind of the same idea. So when I take a look at two functions, for example, y equals 5 to the x and y equals log base 5 of x, I know those two go hand in hand. They cancel each other out. They are inverse functions of each other. So whereas the exponential function of y equals 5 to the x rises quickly, if you flip that on the y equals x, then the log function will rise quickly, but then ultimately slow down its growth, so you don't get that super rapid growth that you do in an exponential function. So, and remember how we find that log is that we take every single point on the exponential and we switch the x and y's, and so you can see that 0, 1 turns into 1, 0, and 1, 5 turns into 5, 1, and so now we have both of those graphs, and they are inverses of each other, again reflected on y equals x. All right, and just some quick examples just for us to review what a log is. So if I asked you, hey, what is the log base 2 of 32 equal, right? A lot of people do this thing where they do 2 to the x equals 32. So really what is happening in the exponent of 2 to give me 32? And you can do it that way, but again, I prefer not to because as the math gets more advanced, I like to look at it as a different way. I like to look at it as, let's think of the inverse of a log base 2, which is 2 to something, 2 to the x, it's 2 to the exponential value. And I'm going to rewrite 32 as 2 to the power of something. So if I rewrite 32 as 2 to the power of 5, now I have the log and the exponential in the same equation, and I get to cancel them out. So ultimately, what does x equal? X equals 5. So what's happening in the exponent? 5 is happening in the exponent. So that's one example. Here comes another example. So again, I'm going to try to rewrite 2 inside of that log as 8 to the power of something. And I know this one's a little tricky, but if you think of the cube root of 8, the cube root of 8 is going to give you 2, and instead of writing it as the cube root, I'm going to write it as 8 to the 1/3 power. And so now notice that log base 8 and 8, they should cancel, and x equals just 1/3. All right, so what's happening in the exponent? 1/3 is happening in the exponent. The exponent of what? The exponent of 8. Okay, and then the last one, I have log 0.001. Now notice I didn't write a base here, and if I don't write a base, then the base is implied, and the base is 10. So we're looking at what we call a common log. You can call it either log, you can call it log base 10, or you can call it common log. All of those are synonymous. So I'm just going to write the 10 there so that we can adjust 0.001. And I'm going to write 0.001 as 10 to the power of something. And in scientific notation, if we move the decimal, we know that that's going to be 10 to the power of -3. And so we have those canceling, and I should get -3. All right, so that's really awesome. Let's move on to now it's just some thoughts about logs to kind of help you understand what is happening in the exponent. So remember, logs and exponents always consider what's happening in the exponent. So I'm going to start off with some examples. We know that if I wanted to multiply like a to the fourth times a to the third, I'm not actually multiplying what's happening in the exponent. For me to simplify a to the fourth times a to the third, I'm actually adding those two things in the exponent, which is kind of an interesting idea. So ultimately I get a to the seventh. So that's a rule that we should know. So essentially when I ask you to do like log base b, which means any b, of 4 times 3, notice I'm multiplying things inside, but ultimately I can add them just like we did in the exponential function. So that's what we call the product rule. So the log base b of m and the log base b of n, if you wanted to add those together, you could just multiply. So notice the multiplying in the exponents means ultimately I have to add those things. So the multiplying in the logs means ultimately I can add those two logs so long as the bases are the same. And that's what we call the product rule. Okay, so let's take this to like if I had a to the 8th over a to the 5. I know that I have 8 and 5 are in the exponent, and if I wanted to simplify it, what would I get, right? And you say, oh, well, you're just going to get 8 minus 5, and that's what we do when we have a quotient, right? And so we're going to do the same thing with logs. If we have a quotient inside of a log, can I separate them? And the answer is yes. And I'm going to separate them by subtraction because that's how I did it in the exponent. And that is called the quotient rule. So in the exponent, you realize that if you're doing division, you can do subtraction to the exponent. So if I'm doing division in my logs, I can do subtraction with my logs. All right, so that's a quotient rule. And this rule is true if the b's are the same. Okay, and finally, one last idea that I have for you is, for example, if I have a power to a power. So if I have a to the 5th and then squared, what do I actually have, right? And so I actually will have whatever 5 times 2 is. I'll have a to the 10th. So notice when I have a power to a power in the exponent, what am I actually doing to the exponent? I'm multiplying those things. So yep, you betcha we have that idea when it comes to logs, because a log is explaining what's happening in the exponent. So if I have log base b, which is log base anything, of 5 squared, then I want to multiply. And how am I going to do that? I'm going to drop that 2 down in the front, and now I'm going to multiply those things together. And so that's what we call the power rule or the power property of logs. So I have something in the exponent, that thing can drop down in front and then multiply by the logs. So notice it's only just explaining what's happening in the logs. So we use these rules just as tools. I know you get a lot of problems that just ask you to manipulate, but ultimately our job is to like apply them when we need them. So for example, if I wanted to solve for 2 to the x equals 14 and I wanted to know what x was, that's kind of tough because 2 to the 3rd is going to be 8 and 2 to the 4th is going to be 16. So x is going to be something that happens to be between 3 and 4. So 3 is in the exponent, 4 is in the exponent. Doesn't quite get me there, so I know that that x value has to be something between 3 and 4. And because I can't take the xth root of it, I'm going to have to do something different. So I'm going to go ahead and use that power property, and I'm going to log both sides of this equation, because remember equation, you got to do it to both sides. That'll let me drop that x down in front and multiply it. And now log of 14 and log of 2, which you can use any base to use this, I'm just going to use a base of 10. Those guys turn out just to be values. You can take the value of them anytime that you want to. I'm just going to turn the log of 14 into 1.46 and then the log of 2 into 0.0301. And that's going to equal x. And so x is going to be 3.8. And we knew it would be a value between 3 and 4. So, and it is a value between 3 and 4. All right, one last example for you. Again, when it comes to solving, so I have this log equation here, and again, I'd like to solve for x. So this time, it's not the exponential I want to get rid of, it's the log I want to get rid of. And I want you to notice that it has a log base of 4. So what gets rid of a log base of 4? 4 to the x gets rid of a log base of 4. So I'm going to put all of this into the exponent of 4. So that exponential function, y equals 4 to the x, I'm going to put all of that into where the x used to be. Why am I doing that? So that the logs and the exponent can cancel each other out, and I get x plus 5 equals 64. Subtracting, I get 59, and now I'm going to plug back in just to check. Okay, so log base 4 of 59 plus 5 equals 3. Is that true? Log base 4 of 64, does that equal 3? And it does, right? So 4 to the third is 64, and that's correct. All right, hope that helped, and just let me know if you need anything else. Thanks a lot.